probability and odds is something you really rely on a lot in real life, but we have a tendency to interchange the two. But the truth is, probability and odds are two separate things. So let's start by talking about probability. If you look at this number line right here, you can see that they list these numbers for probability. 0, 0.25, 0.5, all the way up to 1. Now when we talk about probability, we usually assign a percent to it. And that's kind of, if we change percents to decimals, that's kind of what we're looking here. If we say something has a probability of 1, then it's certain it's going to happen. That's like saying 100%. If we say something has a probability of 0, it's impossible. It's never going to happen. And you can kind of fill in the rest here. If something has a probability of 0.5 or half or 50%, it's going to occur half the time. So the higher your probability, the closer to 1, the closer to 100%, the more likely it is to happen. Whereas it gets closer to 0, the less likely it is to happen. Until it hits 0, though, it doesn't mean it can't happen. It just means that it's not very likely to happen. We have something called theoretical probability. And when we talk about things in theory, we talk about how things should work. Our theoretical probability says the number of favorable outcomes over the number of total outcomes. And here's what we mean by that. We have two coins here. And what if I wanted to know the probability that I would flip two heads? So our probability says the number of favorable outcomes over the number of total outcomes. Well, if we flip this first coin, it could come up heads. I flip the second coin, it could come up tails. I flip the first coin, if it comes up heads again, well, it could come up tails again. But you can see as we flip, it's either going to be heads or tails each time. So if you list all of our outcomes, the first one could be heads, and then we could also have a heads. The first coin could be heads, and the second coin could be tails. Or the first coin could be tails, and the second coin could be heads, or the first coin could be tails, and the second coin could be tails. So if one talks the number of favorable outcomes, favorable means what we want to happen. We want the probability that are both heads. So how many times of all our outcomes here are they both heads? Just this one time here. So the number of favorable outcomes we have is 1. Now what are our total number of outcomes? 1, 2, 3, 4. There are 4 total outcomes. So theoretically, we would think that if we did this experiment, we tossed or flipped 2 coins 4 times, one of the times we would get both heads. That doesn't mean it's going to be like that every time, though. But theoretically, theoretical probability says it should be. We also have experimental probability. And experimental probability means we're actually going to try the experiment now. And we're going to take the number of successes over the total number of times we try it, the total number of trials, to come up with a probability. And we'll be able to use that probability to predict what will happen in the future. So the difference between theoretical probability and experimental probability is that theoretical probability says, in an ideal world, this is what's going to happen. Experimental probability says, we've actually tried it, and this is what has happened. So let's look at an example. It says, toss a coin 10 times. What is the experimental probability of getting heads in this experiment? So let's just say we did it already, and we flip this coin here. And of course it won't work out exactly the first time, but let's say we got heads, tails, heads, heads, tails, heads, tails, tails, heads, heads. We want to figure out the experimental probability. Keep in mind, experimental probability is the number of successes. So what do we want? What do we consider a success? That's going to be getting heads. Over the total number of trials. Well, how many times did we try this? 10 times. So our total number of trials is 10. The number of times we got heads is 6, according to this information here. So our probability is 6 successes out of 10. And if we change that to a decimal, we get 0.6. If you were to change it to a percent, you'd get 60%. So then we could predict in the future that 60% of the time we would get heads. Again, that doesn't mean it's going to happen, but if you go back to the very beginning, 60% or 0.6 would fall in here. So it's going to occur a little bit more than half the time. Let's look at this example. Roll a 6-sided die 5 times. Number cube, dice, whatever. What is the experimental probability of rolling an even number in this experiment? So let's try it. If we roll it 5 times, we'll get a 2, and another 2, and a 4. 2 more times, another 2, and 1 more, a 2. Apparently that's a popular number. So if we wanted to find the experimental probability of rolling an even number in this experiment, remember, the probability of getting an even number is our number of successes, even numbers, over our number of trials. So if we look at this example, we rolled it 5 times, so that's the number of trials. And the number of even numbers, well, in this case, surprisingly, I had 5 even numbers. So our probability in this case is 1 or 100%. Now, according to our opening slide, that means it's certain. That's going to happen every single time. So it's probably a good thing we're doing this example. A lot of times with statistics and probability, information can be skewed. Now in this case, we only rolled it 5 times. Pretty unlikely that they're all going to be even, but not impossible. The more trials you have, the more accurate your data is. So let's just try this again and see what happens. Because common sense should tell us we shouldn't get 100% every single time. So if I roll it, I'm still going to get an even. And again, yay, there's an odd number. And another 4. And a 1, and one more time. And a 6. Okay, so if we, again, just thinking of the same problem here, the probability of getting an even number is our number of successes over our number of trials. Our number of trials was still 5, but this time our number of successes is 1, 2, 3. So our probability is 3 out of 5, which is 0.6 or 60%. Okay. Again, we can use this to predict the future. But notice, and each time we got those 5, the first time I had all 5 were even, the second time I had 3. That's why it's good to have more trials. The more trials you have, the more accurate your data will be. This example here says use the circle graph below showing the responses of 250 college students to a survey asking which factor is most likely to influence your job choice after graduation. If you were asked to ask a randomly chosen college student this question, what is the experimental probability that the student would say type of company? So let's kind of look a little closer at this graph. This graph says influences on job choices. So we have salary, 93 students chose that, location 103, type of company is 37, and size of company is 17. So remember, experimental probability is the number of successes over the number of trials. So we would like the probability, when we talk about successes, we want the probability of type of company. So our success would be how many people chose the type of company. And the number of people who chose the type of company is 37. Our trials, well, how many people were surveyed? If you go back to the information up here, it says they talked to 250 college students. So our number of trials would be 250. If you divide these two numbers here, you just go 37 divided by 250, you're going to get approximately 0.15, okay? Or approximately 15% if you want to think it like that. So if you randomly select someone out of the 250, what is the probability, the experimental probability, that they're going to say their influence is type of company? Well, it's kind of low. It's not impossible, but it's going to happen more times not than that they will say it. Meaning, basically, the chances of you getting someone to say type of company are not very good, although it is possible. So an example like this, pay attention to how many people were surveyed, and then you just have to divide out the successes divided by trials.